Welcome to Boring Stuff. Tonight, let's drift into the hidden world of quantum physics, where uncertainty and wonder shape reality itself. From entangled particles to the secrets inside your body, we'll see how the tiniest mysteries build the universe. So get comfortable, breathe deeply, and let's take a calm journey into the quantum realm together. Where are you right now? Not just your body, your arms resting on a bed or your head settled into a pillow, but you, the tiny thoughts behind your eyes. Maybe you're half awake, half dreaming, hovering in that soft twilight that comes just before sleep takes hold. Maybe you've already drifted a little, your mind skipping from idea to idea like a stone over still water. Wherever you are, I invite you to linger here in this quiet moment and think about something wonderfully strange. The world you see around you, your room, your walls, the warm blanket over your legs. All of it is built from things you can never see. Tiny things behaving in ways that don't make sense if you try to force them into neat, ordinary boxes. There's something comforting about the everyday world. Doors stay closed until we open them. The lamp on your bedside table doesn't flicker in and out of existence when you look away. The walls don't ripple like water. The floor doesn't vanish beneath your feet. We build our lives on these certainties, even though the certainties themselves are illusions stitched together by rules too small to touch. Because underneath it all, everything, your fingers, your hair, the atoms drifting in the air around you, follows the laws of quantum mechanics. And quantum mechanics, though it gives us smartphones and lasers and the warmth of stars, is not tidy or certain. It is a place of maybe, a place of both and, a place where asking a question shapes the answer. The seeds of quantum theory were planted when our most familiar ideas started to fail. In the late 19th century, scientists were confident they understood the building blocks of reality. They could describe the path of a cannonball arcing through the sky, the ripples of sound in the air, even the orbits of planets light years away. Everything seemed orderly, predictable. Cause and effect, input and output. But then cracks began to appear. They found that when they shone light onto certain metals, they saw something unexpected. Electrons popped out. This was the photoelectric effect, and it didn't behave the way classical physics said it should. To explain it, a young physicist named Albert Einstein suggested that light, which had always been described as a wave, could also act like a particle, a photon. Something that should be smooth and continuous was made up of little chunks, discrete packets of energy. This idea was unsettling, but it worked, and it opened the door to deeper strangeness. Imagine a single particle of light passing through two narrow slits cut into a barrier. You might think it would pass through one slit or the other, just like a marble would. But when scientists let many photons pass through the slits one by one, they saw a pattern form on the screen behind, an interference pattern, like ripples overlapping in a pond. This meant that each particle of light behaved like a wave, interfering with itself, taking every possible path through both slits at once, until it was measured. Then the wave collapsed into a single dot on the screen. The simple act of observing changed what was real. This experiment, the double-slit experiment, is something you might have heard of before. It's often brought up because it's such an unsettling reminder that the smallest pieces of our universe don't behave the way marbles do, or billiard balls, or even cannonballs arcing across the sky. They live in a state of possibility until we insist on knowing more, and only then do they settle down, like a shy animal coaxed out of hiding. If you hold your hand up in the dark, you see nothing but shadows. But that hand is buzzing with particles that flicker and dance, that can be in more than one place at once, that can be entangled with other particles half a world away. The everyday objects you trust to stay solid, the floor, the chair, the cup beside your bed, are made up of quantum clouds of uncertainty. And yet, they feel certain. They feel solid. They feel real. How do we reconcile this? How do we hold two contradictory truths, that the world is both solid and shimmering, that certainty is born from uncertainty? The answer, or at least one answer, is that the quantum world is like an endless sea of probabilities. Each particle carries a wave function, a mathematical expression that describes all the possible places it could be, all the possible states it could hold. It's not a ghost story or a magical trick. It's math that works. Math that gives us semiconductors, medical scanners, and computers more powerful than anything our ancestors could have dreamed. And yet, despite its precision, it feels deeply human, because the wave function only collapses, only chooses a reality, when there's an interaction, a measurement, a moment of contact. In this way, reality is participatory. You are not separate from it, floating in a bubble of certainty. You are part of the equation, the observer and the observed, locked in a dance of maybe. If you're listening to this, your eyes closed, your thoughts drifting like a soft current beneath your skull. Consider this. Your brain itself is built on quantum rules. Electrons in the atoms that make up your neurons exist in discrete energy levels. Chemical reactions that pass signals along your synapses depend on the probabilistic dance of electrons tunneling through barriers they should not cross, according to classical physics. The very act of thinking is grounded in the rules of the quantum realm, like music emerging from the vibrations of strings you can't see. Maybe you've heard that we don't really know what quantum mechanics means. And that's true. The math works, the predictions hold, but the meaning behind it all slips through our fingers like water. Some scientists say we shouldn't even ask, that the equations are enough. Others insist there must be an underlying story, something that explains why particles can be here and there, spin up and spin down until we demand to know. And so the questions linger. Is the wave function real, or is it just a tool for prediction? Does the universe split into many worlds, branching into infinite copies every time a quantum event occurs? Is the cat in the box both alive and dead until we peek inside? Or is there a hidden layer we haven't yet seen, a hidden order beneath the chaos? Maybe you find this unsettling, or maybe, like many people do, you find it strangely comforting. Because if the smallest parts of reality can hold so many possibilities, then perhaps the world is more generous than it seems. Perhaps there is room for surprise, room for new paths, even when the old ones feel certain and fixed. As you lie there, the soft hum of your own breath steady and familiar, you are wrapped in these quantum truths, whether you realize it or not. The warmth of your blanket, the light that once streamed from your lamp, the electricity that flows through your phone or computer, All of it runs on quantum rules. Each photon, each electron, each vibrating atom obeys laws that defy common sense and yet hold the universe together with astonishing precision. When you look at the stars, know that the light you see traveled across vast emptiness as packets of energy, sometimes acting like particles, sometimes like waves. That same duality flickers inside every LED, every laser pointer, every fiber optic cable carrying your voice across continents. Long ago, our ancestors looked at the night sky and felt small, surrounded by darkness they didn't understand. Today, we know more. We know that we are not separate from that darkness or from the stars that puncture it. We are built from the same rules, the same patterns, the same shimmering clouds of maybe. The carbon in your bones, the iron in your blood, all of it forged in the cores of stars, carried here by the expansion of the universe, arranged by chemistry that is only possible because quantum physics allows atoms to bond and molecules to form. So, where are you right now? You're here, and yet you are also a ripple in a quantum ocean that stretches to the edges of the cosmos. You are solid, and you are uncertain. You are a conscious observer in a world that responds to the act of being seen. Breathe gently. Let these thoughts drift over you like soft waves. There's nothing to solve tonight, nothing to measure, nothing to collapse into certainty. Only the quiet possibility that the universe, in all its beautiful strangeness, holds you exactly as you are, a tiny flicker of thought, half awake, half dreaming, hovering in the gentle glow of maybe. And tomorrow, when you open your eyes and step back into the world of solid walls and steady floors, perhaps you'll remember that underneath it all, every breath, every step, every heartbeat is stitched together by quantum threads, soft, uncertain, and yet somehow completely real. Imagine you're standing in front of a simple experiment, two thin slits cut into a barrier and a beam of light aimed straight at them. On the other side is a blank screen waiting to catch whatever passes through. It sounds simple, almost boring. Something you might have set up in a high school lab, fiddling with a flashlight and cardboard. But hidden in this simple setup is one of the greatest mysteries ever uncovered about how our universe works when no one is looking. At first glance, the results shouldn't surprise us. You might expect that when you shine light through the slits, you'll see two bright lines appear on the screen behind them, one for each slit, as if you'd thrown sand through two gaps in a fence. But that's not what happens. Instead, you see something stranger, a series of light and dark bands, an interference pattern, as if the light were behaving like water ripples colliding, building up and canceling out. The light acts like a wave. This was already unsettling when scientists first saw it in the early 1800s. Light had been argued about for centuries. Was it a particle, like little grains of sand? Or was it a wave, like sound or water? The double-slit experiment seemed to settle it. Light is a wave. Waves bend, overlap, interfere, and the bright and dark bands on the screen are exactly what you'd expect from ripples on a pond meeting each other. Case closed. Or so they thought. The next twist came a century later, when people like Einstein were forced to admit that light is not just a wave. It also comes in packets, quanta, that we now call photons, So what happens if you send photons through the slits one at a time so they can't interfere with each other? Surely the pattern would change. But it doesn't. Fire one photon at a time, wait long enough, and those single impacts will slowly build up the same interference pattern. The photon, alone, seems to interfere with itself. This is where the ghostly probability creeps in. It's as if the photon explores all possible paths simultaneously, passing through both slits, bouncing around in every possible way. Its probability wave spreads out, a mist of possibilities. Only when it hits the screen, when it's measured, does it snap into a single place. One photon, one dot of light. But over time, all the dots combine into a pattern that reflects every possibility the photon once held. The pattern reveals its wave-like nature, even though each photon hits like a single particle. This is not just a quirk of light. Fire electrons, particles of matter, through the slits instead, and you get the same eerie result. Each electron is tiny, with mass and charge. It shouldn't behave like a wave, but it does. One at a time, they pass through the slits, and over hours or days, they build up the same interference pattern, as if each electron is a ghost exploring every path at once, deciding only at the moment of measurement which version of itself you'll see. What does this mean for you, lying there in the dark, wrapped in a blanket, while your mind drifts through these possibilities? It means that the most ordinary matter, the stuff you're made of, is full of maybe. When you look at your hand, you see something solid. But underneath the skin, beneath the cells and molecules, the electrons in every atom hum with a quantum uncertainty that cannot be pinned down until someone looks. And what does it mean to look? In quantum mechanics, it doesn't mean you, the human observer, peering through a magnifying glass. A measurement is any interaction with the environment that collapses the wave of possibilities into a single outcome. A stray photon bouncing off an electron, a detector flickering, a vibration in the air. Any of these can act as an observation. The universe constantly observes itself, collapsing possibilities into realities over and over. This simple experiment, the double slit, was just the beginning. It showed that our world is built on layers of probability, not certainty. You might think, well, that's just how tiny things behave. Electrons are small. Photons are small. My cup of tea is big and solid. Surely the rules don't apply there. But they do. Or they would, if it weren't for something called decoherence. In your room right now, there is noise. Not just the sound of traffic or the wind brushing against the window, but a deeper noise. Heat, light, vibrations, tiny bits of matter bumping into each other. All this environmental noise destroys quantum coherence for big things. The delicate superpositions that let a photon pass through two slits at once can't survive when billions of particles collide with each other, constantly nudging possibilities into certainty. So your tea stays in its cup. The floor stays under your feet. But at the edges of this classical world, where scientists isolate particles from heat and noise, they see quantum behavior flicker into existence again. They cool atoms to near absolute zero, trap ions in electromagnetic fields, or guide photons through special circuits. There, the ghosts of probability dance freely, and we glimpse the same mysteries that the double-slit experiment first revealed. Consider this: the same rules that make your laptop screen glow, the same quantum leaps that create the interference pattern, are at work inside the microchips and sensors you use every day. The act of switching a transistor on and off, storing a 0 or a 1, relies on quantum tunneling, the ability of electrons to slip through barriers they shouldn't cross, according to classical physics. In that sense, the double-slit experiment is not some dusty curiosity in a lab. It's humming inside your phone, your computer, and your brain. Think, too, of the philosophical ripples that spread from those two slits. If a particle can be here and there, if it exists in all possible paths until observed, what does that say about reality? Is the world out there when no one is looking? Does the moon still hang in the sky if no eyes gaze up at it? Einstein famously struggled with this. He could not accept a universe where God, as he put it, plays dice. He wanted a hidden layer, a deeper cause that would bring certainty back. Many others did too. Some turned to interpretations like hidden variables or many worlds, each trying to explain how a photon can split itself like a ghostly trick. But for all the interpretations, the experiment remains the same. A beam of light, two narrow slits, a screen. A pattern that builds up dot by dot, photon by photon, each impact a tiny act of chance adding up to a larger, inevitable wave. This is quantum mechanics, certainty made from uncertainty, pattern from chaos, logic from something that seems at first glance to defy it. And so, as you lie back tonight, breathe in this idea. Beneath every wall and window, beneath every pillow and cup, there is a world built on waves of maybe. A world where the simplest things, a light beam, a metal slit, reveal the most profound truth: that existence itself is a ghost story written in the language of probability. Let your mind drift there, if you like. Imagine you are a photon, flitting through the darkness. You approach the barrier, and in that moment, you don't choose one slit or the other. You choose both. You ripple through every possible path, exploring all futures, all presents. Only when you arrive at the screen do you become one thing again. The observer sees you, and you settle down into certainty. And when you wake up tomorrow, remember this small magic. The double slit is not a trick or a puzzle to solve before sleep. It is a reminder that the world is not as solid as it seems. That your breath, your thoughts, your heartbeat, all of them arise from particles that obey this same ghostly rule. You are a pattern of maybe, stitched together by observation, by interaction, by the quiet collapse of wave after wave after wave. So, rest easy tonight, knowing that even if the world feels certain, its certainty is built on shadows of possibility. Somewhere, in the flicker between here and there, you too are passing through your own slits, choosing your paths, your future still a shimmering pattern waiting to be seen. Close your eyes for a moment and imagine two tiny particles, perhaps two electrons, born together in some hidden corner of the universe. Maybe they emerged from a single atom splitting apart, or from a collision in a lab so small it fits on a fingertip. Now imagine that these two particles drift away from each other. One floats off to the left, the other to the right. They travel for meters, kilometers, perhaps even across light years, if you let your mind stretch that far. And yet, in a way that baffles our everyday sense of how things should work, they remain connected, as if an invisible thread runs between them, humming softly through the emptiness of space. This delicate connection is quantum entanglement, a phenomenon so strange that even Einstein, who helped birth the ideas of quantum mechanics, found it unsettling. He famously called it spooky action at a distance. And who can blame him? In the world you and I know, if you push a ball, it rolls away. If you flip a coin, it lands on heads or tails, but does so alone. We expect the world to be local, that things only affect each other when they touch, or when a force travels between them at a speed we can measure. But the quantum world doesn't always play by these rules. When two particles become entangled, they share a quantum state. That means certain properties, like their spin, their polarization, their angular momentum, are linked in a way that goes beyond mere correlation. If you measure one particle and find its spin is up, you instantly know the other must be down, no matter how far apart they are. It doesn't matter if the other particle is a lab bench away or on the far side of the Milky Way. The result is the same, instant and perfect, as if the universe whispers the answer from one particle to the other in no time at all. At first glance, you might think, this must be a trick. They must be carrying hidden instructions, a secret plan they agreed on before they parted ways. And for a long time, physicists argued about exactly that. Maybe particles really did have hidden variables tucked away inside them, invisible switches that determined how they would respond when measured. But in the 1960s, physicist John Bell devised an elegant mathematical test, Bell's theorem, that showed this kind of local hidden plan couldn't explain what we observe. Over decades, experimenters tested Bell's ideas with exquisite care, sending entangled particles through fibers, bouncing them off mirrors, isolating them from any possible outside influence. Again and again, the results have agreed with quantum predictions. The connection between entangled particles is real, and it is non-local. It doesn't mean information can travel faster than light. Nature has safeguards for that. You can't send a message to your friend on the other side of the universe just by measuring your particle. The outcome of each measurement is random. You only see the connection when you compare your results afterward, using good old classical communication. But still, something profound is happening. The universe, at its tiniest scales, weaves together things that seem separate. It ties a knot between distant particles, a knot that holds fast until disturbed. What does that mean for you, lying in the dark, listening to this soft story unfold? It means that your world, your daily life of keys and coffee mugs, is built on a foundation where distance is not always what it seems. Somewhere deep down, the particles that make up your cells, your brain, your memories, might once have been entangled with others. Most of that entanglement is lost to decoherence, that gentle unraveling that happens when particles bump and jostle and heat up and share their secrets with the wider world. But at the very edges of physics, in isolated labs cooled near absolute zero, we see entanglement persist, a window into a realm where connections run deeper than space itself. Scientists are learning to tame this spooky bond. Quantum computers, still young and experimental, hope to harness entanglement to link qubits together. It's what allows quantum error correction, a kind of whisper network between particles that lets them detect when a fragile state has been disturbed. Entanglement is also at the heart of quantum teleportation. No, not teleportation like Star Trek, beaming people from ship to planet, but teleportation of information, a way of transferring the state of one particle to another far away, using entanglement as the bridge. In 1997, scientists performed the first quantum teleportation experiment in the lab. They entangled two photons, separated them, and then used a third photon to imprint a quantum state onto one of them. The original state was destroyed, but instantly, the distant photon adopted that state, like a perfect handoff in a cosmic relay race. Since then, researchers have teleported quantum information over kilometers of fiber optic cable and even between satellites orbiting Earth. Someday, this delicate exchange could become the backbone of quantum communication networks, unhackable channels that use the laws of physics themselves as a lock and key. But entanglement doesn't just stay in the lab. It nudges at the edges of our biggest questions about reality itself. In the 1930s, Einstein, Podolsky, and Rosen, three titans of physics, proposed what's now called the EPR paradox. They hoped to show that quantum mechanics must be incomplete, that spooky action couldn't be the final word. But experiments have confirmed time and again that the quantum world is indeed non-local, that the fabric of reality is stitched together by threads we can't see or touch, but which bind the distant and the near in ways our everyday intuition struggles to grasp. Imagine for a moment that your mind is like an entangled pair of particles. You listen to these words, your thoughts drift outward, touching memories, ideas, dreams. Each thought leads to another, sometimes far apart, yet deeply connected. In this way, your inner world mirrors the quantum world, distant, yet entangled. The more you learn about these ghostly bonds, the more you might feel a quiet sense of kinship with the universe. You, too, are stitched together from parts that communicate silently across time and space. Your cells, your memories, your stories. Some philosophers have wondered if entanglement might play a role in life itself. Could the delicate dance of molecules inside your cells, or the photosynthetic processes in plants, rely on quantum coherence and entanglement? It seems improbable. The warm, wet environment of biology usually destroys quantum effects. And yet, experiments hint that in certain cases, like the migration of birds or the transfer of energy in leaves, quantum entanglement might be quietly at work, helping nature navigate the complex web of existence. So tonight, as you rest your head and let your thoughts drift like those particles, think of the universe as a vast network of possible connections. Some break and tangle in the noise of daily life, but others endure. Bonds that hold stars together, that let particles talk to each other across light years, that allow the very fabric of space to hum with quiet coherence. Maybe, just maybe, we too are entangled in our own human way. A family sharing laughter across phone lines, friends thinking of each other at the same time, people who have touched each other's lives in ways that cannot be undone. Perhaps this is only poetry, but then again, the quantum world reminds us that reality is stranger than fiction, and sometimes poetry is the best tool we have to glimpse its depths. So breathe easy now, in the soft darkness. Let the image of two distant particles still holding hands across the emptiness, soothe you. Let the thought that our universe, so wide and cold and ancient, is woven together by invisible threads, bring you a quiet sense of wonder. In a world built on connections that defy distance, perhaps you are never truly alone. Somewhere, in the hush between your heartbeat and the stars, the universe is entangled with itself, and with you. Let your eyes close now, if they haven't already, and picture a computer. Not the warm rectangle glowing on your desk, or the sleek phone by your side, but something stranger, colder, quieter. Imagine a machine humming in a sealed chamber, so cold that the air inside would freeze instantly if you opened the door. Inside this frigid sanctuary, tiny qubits, the building blocks of a quantum computer, hold their breath, balanced delicately between what is and what could be. A classical computer, the kind you're using now, is a marvel in its own right. Millions upon millions of tiny switches, called transistors, open and close in precise patterns, processing information at breathtaking speeds. Everything you see on your screen, every word you type, every video you watch, is built from simple bits, zeros and ones, yes or no, true or false. A bit can be in one state or the other, but never both. The quantum world, though, has no such sharp boundaries. Here, a qubit can be a 0, a 1, or, in its special quantum way, both at once, a shimmering possibility called superposition. Picture a coin spinning in the air. While it spins, it is neither heads nor tails, or perhaps you could say it is both, waiting for the moment it lands. In a quantum computer, the coin never lands until you look. It stays in that suspended dance, exploring multiple possibilities at once. This is the key to quantum computing's promise. Every additional qubit doubles the number of states the system can explore simultaneously. 2 qubits can represent 4 possibilities at once. 10 qubits, over 1,000. 20 qubits, more than 1,000,000. 50 qubits, a mind-boggling quadrillion possibilities, all held delicately within a single machine. Imagine a library so vast that it contains every possible book, every combination of letters ever written. And imagine reading all of those books at once, understanding every story in parallel. This is the poetry at the heart of quantum computing. But what does this parallelism mean in practice? It doesn't mean a quantum computer can magically solve any problem instantly. Like everything in the quantum world, it's more subtle than that. Quantum computers are not better than classical ones at every task. They are better at certain types of problems, the ones that involve complex, tangled webs of possibilities. These include optimization tasks, where countless variables must be balanced just right, or factoring large numbers, a problem that underpins modern cryptography, or simulating quantum systems themselves, using quantum mechanics to understand quantum mechanics, as if water could be used to study waves. Imagine you have a maze with trillions of paths, only one of which leads to the exit. A classical computer would check each path one at a time, incredibly quickly, but still step by step. A quantum computer can, in a sense, explore many paths simultaneously, using interference, the same wave-like behavior that makes electrons slip through two slits at once, to cancel out the wrong paths and amplify the right one. The result emerges when the quantum state collapses, like a whisper becoming a word. One famous example is Shor's algorithm, developed by mathematician Peter Shor in the 1990s. It showed that a quantum computer could factor large numbers exponentially faster than any known classical algorithm. This matters because much of modern internet security relies on the difficulty of factoring large numbers. Break that, and you break the locks on our digital world. For now, these quantum locks remain theoretical. Today's quantum computers are far too small and fragile to crack them. But they are growing steadily, qubit by qubit, as researchers around the world cool them, shield them, and coax them into coherence. Coherence. That word keeps returning in the quantum story. It means keeping the delicate quantum states undisturbed, preserving superposition and entanglement long enough to do meaningful work. But quantum systems are easily disturbed by the slightest touch. A stray photon, a whisper of heat, a tremor in a magnetic field. This fragility is called decoherence, and it is both the enemy and the teacher of quantum computing. To keep qubits coherent, they must be isolated from the world, bathed in temperatures colder than deep space, shielded from noise. It's like trying to keep a soap bubble intact while the winds howl outside. Different quantum computers use different physical systems to build qubits. Some use trapped ions, individual atoms held in place by electric fields, manipulated with laser pulses. Others use superconducting circuits, tiny loops of metal that carry current with zero resistance, cooled to fractions of a degree above absolute zero. Still others experiment with photons of light, using their quantum states to encode information that can travel along optical fibers. Each approach has its strengths and weaknesses, and there is no universal agreement yet on which one will win the race to practical quantum computing. It's not unlike the early days of classical computing, when engineers tried vacuum tubes, punch cards, and magnetic tapes, each new idea building on the last until the sleek silicon chips of today emerged. Quantum computing is in its bicycle stage, ingenious but wobbly, full of potential but still far from the rocket ships we dream of. Yet despite this youth, progress is steady. Companies, universities, and national labs around the world are building quantum processors with dozens of qubits. Researchers have demonstrated small-scale quantum error correction, entanglement swapping, and even rudimentary quantum networks, tiny, chilly test beds for a future quantum internet. Some quantum computers can even be accessed through the cloud, so you, lying in bed tonight, could connect to a quantum machine humming away in a distant lab and run an algorithm that dances with superposition. But what happens when these machines grow up? What problems could they help us solve? One of the most exciting is simulating quantum systems themselves. Ironically, quantum mechanics is incredibly hard to simulate with classical computers. The number of variables grows so rapidly that even the most powerful supercomputers choke on the math. But a quantum computer, by its very nature, follows the same quantum rules. It's like using waves to understand waves, or using the ocean to map the currents within it. This could revolutionize fields like chemistry and material science. Imagine modeling the behavior of complex molecules with unprecedented precision, designing new medicines, more efficient solar panels, or batteries that store more energy with less waste. It could help us understand superconductivity, that mysterious state where electrons flow without resistance, and maybe unlock ways to harness it at room temperature. It could reveal the secrets of exotic materials, quantum magnets, or even the behavior of particles at the edge of black holes. Quantum computers also hold promise for optimization problems, the sort that underpin logistics, finance, and artificial intelligence. From finding the most efficient routes for delivery trucks to balancing massive financial portfolios or training better machine learning models, these machines could do what classical computers struggle to do in any reasonable time. And yet, through all this, there is something oddly poetic about quantum computing. It asks us to think not in certainties, but in probabilities. It blurs the line between hardware and mathematics, between what is and what might be. It takes the ethereal principles of superposition and entanglement, ideas born from the strange depths of quantum physics, and turns them into tools for discovery. In doing so, it reminds us that our greatest technologies often emerge from our deepest questions. When you pick up your phone tomorrow or open your laptop, you'll be using the descendants of ideas that once seemed impossibly abstract. The transistor, the laser, the chip, all born from the early quantum revolution. Quantum computing is simply the next chapter in that story, the next step in our quest to bend the strangeness of the quantum world into something useful, something astonishing. So let your thoughts drift now, like qubits in superposition, balanced delicately between dreams and waking. Picture that chilly chamber, deep underground or high in a research tower, where a quantum computer hums softly. Inside, particles exist as clouds of maybe, linked together in invisible knots of entanglement, exploring vast landscapes of possibility all at once. Maybe one day, the answers to our hardest problems, curing diseases, feeding billions, unlocking new forms of energy, will emerge not from linear calculation, but from machines that think in probability. Machines that, in their own quiet way, dream in the language of the quantum world. Until then, these fragile bubbles of possibility remind us of something profound, that the universe is not made only of certainty and solid ground, but of uncertainty, curiosity, and the patient work of those who dare to listen to its faintest whispers. Sleep now, if you wish, wrapped in the thought that somewhere in the cold, a machine is holding 1,000,000 possibilities in its grasp, balanced between what is and what could be. And perhaps, in its shimmering quantum heart, a piece of your own wonder drifts quietly beside it. Settle in a little deeper now. Let your breathing slow, your thoughts soften, as we wander from the realm of machines cooled to near absolute zero into something warmer, wetter, and unexpectedly alive. Life. Plants reaching for the sun, birds crossing continents guided by invisible maps, your own body, each cell a bustling city of molecules, all orchestrated in perfect, miraculous order. For decades, we separated the quantum world from the world of biology. Quantum mechanics seemed the realm of particles and labs, cold and sterile. Biology seemed too messy, too warm and noisy for delicate quantum effects to survive. And yet, as scientists have peeked closer, something astonishing has emerged. There is a growing sense that life itself might be quietly harnessing quantum phenomena, that deep inside the green of a leaf, the eye of a robin, or the fragrance of a rose, quantum rules might be whispering their secrets. This field of study, still new and full of mystery, is called quantum biology. Let's begin with something beautifully simple: a leaf. Every blade of grass, every flower petal, every towering tree depends on photosynthesis, the process that turns sunlight into food, the alchemy that feeds nearly every living thing on Earth. You might picture sunlight as warmth on your face, but at the smallest scale, it is photons, tiny packets of energy traveling from the sun to the chlorophyll molecules in a leaf. When a photon strikes a chlorophyll molecule, it excites an electron, creating what scientists call an exciton, a shimmering bundle of energy. This energy must find its way to the reaction center, the tiny engine deep within the leaf, where this light energy is transformed into chemical energy, stored away as sugars that power the entire plant. In a world without quantum magic, this journey might be wildly inefficient. The energy would bounce randomly from molecule to molecule, like a marble dropped into a maze, ricocheting until it found its target, or didn't. But the evidence suggests something far stranger happens. Researchers have discovered that the exciton doesn't simply choose one path. Instead, it explores many paths at once, thanks to a phenomenon called quantum coherence. It's as if that marble, instead of rolling down one path, splits into countless marbles, each testing a different route simultaneously. The shortest, most efficient path emerges from this quantum dance, allowing plants to transfer energy with nearly perfect efficiency. Experiments using ultra-fast lasers and delicate spectroscopy have detected these quantum signatures, lasting longer than anyone once thought possible inside the warm, wet, noisy environment of a living cell. Nature, it seems, has found a way to protect fragile quantum states and use them to power the very process that makes life possible. And photosynthesis is only the beginning. Let's lift our eyes now and imagine the sky filled with migrating birds. Every year, birds like the European robin fly thousands of kilometers, traveling across continents with astonishing precision. They have no GPS, no magnetic compass in their pocket. Yet they find their way, year after year, generation after generation. For a long time, scientists puzzled over this. How do birds sense the Earth's magnetic field? One leading theory is that they do it through a kind of quantum compass hidden in their eyes. The key may lie in special light-sensitive proteins called cryptochromes. Here's how the idea works. When a photon of light hits the cryptochrome molecule, it knocks an electron loose, creating what's called a radical pair. Two electrons, each on a separate molecule, with their spins quantum entangled. The Earth's weak magnetic field subtly influences how these spins evolve, shifting the balance between their quantum states. This tiny shift changes the chemistry inside the bird's retina. The bird may quite literally see the magnetic field as a pattern of light and dark, a visual overlay that guides it across oceans and forests. It's a delicate dance, one that depends on quantum entanglement, a phenomenon so fragile it's hard to maintain even in a carefully shielded lab. Yet nature may be doing it inside the eye of a tiny bird, thousands of meters in the sky, every night and day. If true, and experiments have given tantalizing hints, then every robin perched on a branch is a living quantum navigator. Now, let's come a little closer to home, to you and me, and to the simple, overlooked act of breathing in a scent. Imagine walking past a rose bush in summer, the fragrance of a single bloom drifting into your nose. How does your brain know that scent? The traditional theory is shape-based. Odor molecules drift in, bind to receptors like keys fitting into locks, and your brain decodes the pattern. But the story may be more interesting. Some researchers have proposed that your nose doesn't just detect shapes, it listens to vibrations. This idea, called the vibrational theory of smell, suggests that when an odor molecule binds to a receptor, it vibrates at specific frequencies. If the vibration matches just right, it allows electrons to quantum tunnel, jumping across a barrier they couldn't cross otherwise. This electron jump triggers the signal that tells your brain, this is rose, or coffee, or fresh-baked bread. Quantum tunneling is the same trick that lets particles slip through barriers in nuclear fusion, the same trick that powers the sun. And yet, in this theory, it's happening inside your nose, every time you breathe in the scent of a flower or a warm cup of tea. Quantum biology is still a young science. Many of these ideas are still debated, still waiting for more evidence. Some experiments support them, others raise questions. But even the possibility that life harnesses quantum effects is a gentle reminder that biology is not separate from physics. It is woven into it, atom by atom, wave function by wave function. And what about the most profound mystery of all? Your mind. Some scientists have wondered whether the quantum world plays a role in consciousness itself. Could your thoughts be shaped by quantum processes happening deep inside your brain? One theory, known as OR, was proposed by the physicist Roger Penrose and anesthesiologist Stuart Hameroff. It suggests that tiny structures inside your neurons, called microtubules, could support quantum states. These states might allow information to be processed in ways that classical biology cannot explain, perhaps giving rise to the unique flow of conscious experience. This idea is controversial and far from proven. Many neuroscientists remain skeptical. The brain is warm, wet, and chaotic, conditions thought to be deadly for fragile quantum coherence. And yet, the mere possibility is compelling enough to keep some researchers looking deeper, asking whether quantum mechanics might help answer questions about perception, free will, or the very feeling of I am. Whether consciousness is quantum or not, the idea nudges us to remember how deeply connected everything is. The carbon in your cells was forged in stars, bound together by the quantum bonds that make molecules possible. The signals in your brain rely on the chemistry of neurotransmitters, shaped by the Pauli exclusion principle that keeps electrons in their proper places. Every thought, every breath, every heartbeat is an echo of the quantum rules that shape reality. So, as you lie here tonight, drifting further into rest, imagine this. You are a collection of particles, each obeying the strange, beautiful dance of quantum mechanics. You are built from atoms that tunnel, electrons that exist as shimmering clouds of possibility, molecules that hold together because quantum laws say they must. Perhaps, deep inside the cells of your body, quantum effects guide processes in ways we are only beginning to glimpse. Or perhaps they wait for future generations to discover. Either way, the thought is comforting, that life, in all its warmth and messiness, might be a quiet symphony played on the strings of the quantum world. Next time you stand under a tree, think of the sunlight filtering through its leaves, photons striking chlorophyll, creating quantum excitons that find their way with impossible efficiency. Next time you see a robin perched on a fence, imagine the magnetic field shimmering invisibly in its eyes, entangled electrons whispering directions that guide it home. Next time you breathe in the scent of a rose, remember that, perhaps, a tiny quantum leap is bringing that fragrance to life inside your mind. And when you close your eyes, as you are now, remember that you, too, are a quantum story, a pattern of probabilities, a tapestry of entanglements, woven together by evolution, physics, and the quiet hum of the universe's most delicate secrets. Life does not merely survive the strangeness of the quantum world. It dances with it. It listens for its whispers. It may even dream with it, just as you are dreaming now, drifting deeper into a sleep where everything is connected. Leaf, bird, breath, thought, all bound by the hidden heartbeat of quantum wonder. Let's stay right here, resting in this quiet space between your thoughts and the universe itself. You've drifted with me from the fragile coherence inside quantum computers to the hidden quantum secrets in leaves and birds and your own mind. Now, let's gently tilt our heads back and look up, way up, to the stars, to the black depths of space, to the swirling birthplaces of galaxies. It's tempting to think that the quantum realm lives only in the tiny, electrons, photons, particles flickering in and out of certainty. But the truth is more astonishing. The universe itself is built on quantum rules. The same mathematics that governs an electron dancing around a nucleus also governs the fire in the hearts of stars and the shape of the galaxies that spin silently through the dark. So lie back, take another slow breath, and imagine this: the solid ground beneath you, the moonlight drifting through your window, the endless sky above, all of it hums with quantum music. The fabric of the cosmos is woven from probabilities, entanglements, and delicate laws that defy everyday logic. Let's begin small, with the building blocks of everything. Picture an atom, tiny beyond comprehension, mostly empty space. A nucleus of protons and neutrons surrounded by a cloud of electrons. If you could shrink yourself down to the scale of that electron, you wouldn't see it circling neatly like a planet around the sun. You'd see something stranger, a shimmering cloud of maybe, a fuzzy orbital where the electron is likely to be. Why does it stay there? Because of quantum mechanics. The Schrödinger equation describes the wave function of the electron, its ghostly probability field. And that wave function obeys strict, beautiful rules. Only certain energy levels are allowed. Electrons can't just hover anywhere they please. They must snap into place like musical notes on a scale. It's this quantization, this all-or-nothing nature, that gives the world structure. Without it, atoms wouldn't exist. Hydrogen wouldn't be hydrogen. Water wouldn't form. Your body wouldn't hold together at all. One principle is especially important: the Pauli exclusion principle. Discovered by Wolfgang Pauli in the early 20th century, it says that no two electrons can occupy the same quantum state at the same time. Imagine a cosmic dinner party with infinite chairs, but no two guests are ever allowed to sit in exactly the same chair. This rule forces electrons to fill up orbitals in specific patterns, stacking into shells that create the rich diversity of chemical elements. Without the Pauli principle, matter would collapse in on itself. You could pass through walls. Your hand would sink into your desk like a ghost. The firmness you feel when you press your palm on your chest, that's electrons refusing to share states, pushing back against each other with invisible quantum force. So quantum mechanics shapes the smallest things, but its influence doesn't stop there. Let's drift further out, to the stars overhead. Inside the hearts of stars, quantum rules allow fusion to happen. Imagine the sun. That bright, steady warmth on your face is actually a furnace where hydrogen atoms are forced together under immense pressure and temperature. But here's the twist. Classically, they shouldn't have enough energy to overcome the repulsion between their positively charged nuclei. They should bounce apart like magnets turned the wrong way. Yet they fuse. How? Quantum tunneling. The protons don't go over the energy barrier. They slip through it, like a ghost passing through a wall. This improbable leap happens countless times every second in the sun's core, releasing the energy that lights your days and grows your food. Without quantum tunneling, the sun would be dark. So the sunrise is, quite literally, quantum magic at work. Now follow that sunlight as it crosses space, traveling millions of miles to reach Earth. Photons, the quanta of light, travel as both waves and particles. They can interfere with each other, bend around obstacles, and arrive here, touching your skin, warming your face. Each photon, a final note in a journey that began in a quantum leap at the sun's core. When a star exhausts its fuel, quantum mechanics steps in again. Some stars collapse into white dwarfs, incredibly dense balls of matter no bigger than Earth, but as heavy as the sun. What keeps them from collapsing further? Electron degeneracy pressure, another name for the Pauli exclusion principle. The electrons inside refuse to be squeezed into the same state, and that refusal holds up the star against the pull of gravity. If the star is more massive, the story goes deeper. It can collapse into a neutron star, where not just electrons, but even protons and neutrons are crushed together. Here, quantum rules for fermions. Particles like electrons and neutrons create a new kind of pressure, neutron degeneracy pressure, that stops the collapse. The densest neutron stars pack the mass of the sun into a sphere only 20 kilometers across, so dense that a single teaspoon would weigh billions of tons. And if a star is even heavier still, no quantum pressure can save it. Gravity wins. The star collapses into a black hole, a place where our understanding of quantum mechanics and gravity strains at the seams. Inside a black hole, we suspect that space and time themselves are twisted by quantum effects, a tantalizing clue that the universe's two great theories, quantum mechanics and general relativity, may one day be joined into a single elegant framework. Some physicists are working on just that, a theory of quantum gravity, a grand unification that could explain what happens inside black holes, or what happened at the moment of the Big Bang, when the entire universe was compressed into a quantum seed smaller than an atom. And that's where the quantum story of the cosmos reaches its greatest scale. In the first moments after the Big Bang, the universe was a frothing, seething quantum field. Fluctuations, tiny random variations, popped in and out of existence. Inflation, a period of rapid expansion, stretched these fluctuations across vast distances. These tiny quantum ripples became the seeds of galaxies, stars, and planets. Look up at the night sky. Every swirl of stars, every galactic arm, traces its history back to a jitter in the quantum foam, frozen and magnified into the grand structures we see today. So the universe is quantum all the way up, from the ghostly electron hiding in a hydrogen atom to the swirling dance of galaxies. The same rules hum quietly underneath. It's strange to think about. The solidity of your chair, the warmth of your tea, the heartbeat in your chest, all are built on a foundation of uncertainty and probability. A table is stable because its atoms are stable. Its atoms are stable because electrons obey quantum laws. The large emerges from the small, the certain from the uncertain. And here you are, lying quietly, drifting into the edges of sleep, a being made of stardust, atoms forged in stars, molecules held together by quantum bonds, thoughts drifting like wave functions through your mind. The distance between you and the stars is smaller than you think, because the same math shapes both. This is what makes quantum mechanics so quietly revolutionary. It doesn't just rewrite the rules for the tiniest particles. It tells us that reality is participatory. The world doesn't stand still, waiting to be observed. It hums, it dances, it flickers between possibilities. And when you look, when any measuring device interacts, it chooses, collapsing maybe into here and now. So the next time you step outside and look at the sky, remember, the starlight that touches your skin is a gift from quantum tunneling deep in a fusion core. The solid ground beneath your feet holds you up because electrons refuse to share quantum states. The breath you draw carries oxygen, a molecule shaped by the precise geometry of electron orbitals. You are living proof that the quantum realm isn't separate from everyday life. It is the foundation of it. And if the universe is quantum all the way up, maybe your dreams tonight are too. Each thought, each memory, each gentle drift into sleep might echo the same delicate, interconnected dance of probabilities. Like the wave function of an electron, your dreams shimmer between states, exploring what could be before settling into what is. You are not separate from this story. You are a quantum creature, built of patterns that extend from the smallest particles to the widest reaches of space-time. The next time you think the universe is far away, remember, it's right here, in the spin of an electron, the warmth of a photon, the delicate balance of forces that hold your atoms together. Rest now, if you like, or drift with me a little longer as we follow the quantum thread from the edge of the observable universe back to the next layer of mystery, the strange experiments that reveal just how deeply entangled everything truly is. So here you are, drifting gently on this slow river of thought, your mind perched somewhere between the stars overhead and the electrons swirling within you. Maybe your eyes are closed. Maybe you can feel your breath, soft and steady, a little quieter now. And maybe you're wondering, how do we actually know all this? These strange claims, particles that are here and there, photons slipping through two slits at once, entanglement binding distant things like invisible thread. It's one thing to describe the math, the neat chalk marks on a physicist's blackboard. But quantum mechanics didn't remain an idea scribbled in notebooks. It revealed itself through experiments, clever, delicate, sometimes mind-bending experiments that forced us to accept the uncomfortable truth. Reality is not what our intuition says it is. so settle in. This is the part of our story where we peek into real labs, the famous paradoxes and setups that still make students raise their eyebrows and whisper, "Can this really be true?" Let's begin with an old friend, the double-slit experiment. This is the grandparent of all quantum mysteries, the simple, elegant test that exposes the heart of quantum weirdness. Picture it in your mind. A beam of particles, photons, electrons, even entire molecules, aimed at a screen with two narrow slits side by side. Beyond the slits is a detector screen that registers each particle that arrives. Classically, you'd expect that each particle passes through one slit or the other. Like tiny bullets, they'd make two bright spots behind the slits, matching their paths. But that's not what happens. Instead, what appears on the screen is an interference pattern, a series of light and dark bands, exactly like what you'd get if waves were passing through both slits and interfering with each other. So an electron, a single, solid-seeming particle, seems to go through both slits at once, behaving like a wave. If you fire the particles one at a time, so only one electron travels at any given moment, the pattern still appears. Each individual electron interferes with itself. But here's the twist. If you put a detector by the slits to see which slit the electron actually goes through, the interference pattern disappears. The electron stops behaving like a wave and acts like a particle again, leaving two spots behind the slits, no bands. The act of measuring which path the electron takes collapses its wave function, destroying its ability to interfere. Reality shifts based on whether you ask the question. This is the essence of quantum weirdness. The experiment's outcome depends on what you choose to observe. Physicists have repeated this experiment countless times, with electrons, photons, even giant molecules made of hundreds of atoms. The result never fails to astound. At the smallest scales, nature is not a fixed story waiting to be read. It's a shimmering cloud of possibilities that solidifies only when you interact with it. And this is just the beginning. Let's drift deeper into the quantum forest and meet Schrödinger's cat, the most famous feline that never existed. Erwin Schrödinger, one of the founding fathers of quantum mechanics, invented this thought experiment in the 1930s to illustrate how strange the theory becomes when you scale it up to everyday objects. In the thought experiment, a cat is sealed in a box with a radioactive atom, a Geiger counter, a vial of poison, and a hammer. If the atom decays, the counter triggers the hammer, which breaks the vial, releasing poison that kills the cat. If the atom does not decay, the cat lives. Quantum mechanics says that until you open the box and check, the atom is in a superposition, both decayed and not decayed. So the cat, absurdly, is both dead and alive. Schrödinger's point wasn't to suggest that zombie cats roam the universe in limbo, but to highlight the measurement problem. When does a quantum system stop being fuzzy and become definite? Is it when a particle interacts with a detector? When a human looks at the result? Is there a difference between the two? This puzzle still fuels debates today. Some interpretations suggest the cat splits into two worlds, one where it lives, one where it dies. Some say the wave function collapses on its own, without needing an observer. Others wonder if consciousness itself is somehow involved. From the cat, let's step into the even stranger realm of entanglement, what Einstein famously called spooky action at a distance. Imagine two particles that interact in such a way that their quantum states become linked. You could separate these particles by light years, yet when you measure one, you instantly know something about the other. In the 1960s, physicist John Bell devised a test to see if entangled particles really do share information faster than light, or if some hidden variables could explain the correlations. Experiments over the decades, the so-called Bell test experiments, have shown again and again that entanglement is real. No local hidden variables can explain the results. When you measure one particle's spin, the other's spin snaps into place, even if it's far away. Yet this connection can't be used to send a message faster than light, because the outcomes are random. The universe whispers between the particles, but not in any way that breaks Einstein's speed limit. And so, at the heart of the quantum world, you find these paradoxes. A particle that is both here and there, a cat that is both alive and dead, a pair of particles that act like twins, sharing secrets across the void. These aren't philosophical games. They're tested, confirmed by experiments over and over, pushing the limits of our understanding. And the mysteries go deeper still. Physicists are designing even stranger tests. The quantum eraser experiment, for example, takes the double-slit paradox a step further. In this setup, the which path information of a photon is marked in a subtle way, but later, that information can be erased, restoring the interference pattern. Even more baffling, the decision to erase or not erase can be made after the photon has passed through the slits, implying that future choices can influence past behavior. This doesn't mean you can rewrite history, but it does mean the quantum world laughs at your neat idea of before and after. Then there are tests of macroscopic superpositions, scientists coaxing bigger and bigger objects into quantum states. Researchers have put tiny mirrors and mechanical oscillators into states where they vibrate in two opposite directions at once. They've cooled objects to near absolute zero, hoping to see if quantum strangeness scales up. So far, decoherence, the tendency for quantum states to collapse when they interact with the environment, makes it fiendishly hard to keep large objects in superposition. But the quest continues. Why do we chase these paradoxes? Because they're keys to unlocking what quantum mechanics is really telling us. They drive new ideas about how to build quantum computers, machines that use superposition and entanglement to perform calculations that would take classical computers billions of years. They spark questions about quantum gravity, how to marry the fuzzy laws of particles with the smooth geometry of space-time. They challenge our ideas of reality, time, and causality. It's humbling to think that every time you open your eyes, every time you measure the world in any way, you play a tiny part in the universe's ongoing collapse from possibility into certainty. You're like the detector in the double-slit experiment, the observer who turns the maybe into the here and now. Yet there's something quietly comforting in this too. The experiments remind us that the universe isn't frozen or finished. It's alive with potential, a story that unfolds only when you peek inside the box. Your life, your choices, your thoughts, they're part of this participatory reality. You are not a spectator to the quantum world. You're woven into it. And so, as you lie there, letting your mind drift on the edge of sleep, imagine those lab benches glowing under soft lights, the delicate detectors waiting for a single click, the particles streaming one by one through slits cut by human hands. Think of all the people, from Schrödinger and Bohr to the young students today, who stand before these paradoxes and whisper, "How can this be?" They build better detectors, colder traps, cleverer tricks to tease out answers. They catch glimpses of a world that defies our common sense, but holds a deeper, hidden logic. One day, maybe you or someone you know will step into that lab, nudge that experiment forward, and find a new piece of the puzzle. For now, rest easy in the knowledge that reality is stranger than we can yet grasp, and that strangeness is a gift. It means there is always more to learn, more to explore, more to wonder about as you drift through the soft darkness of your own mind. And when you wake, the paradoxes will still be there, waiting like unopened books on a shelf, reminding you that beneath every ordinary moment, quantum possibilities hum quietly, shimmering, just waiting for you to notice. So here we are, you and I, still drifting on this slow current of quantum wonder. We've seen how particles defy our neat expectations, how entangled pairs whisper secrets across the cosmos, how the simple act of looking can flip a wave of possibilities into a single, settled fact. But now, imagine turning that question back toward yourself. If an electron's reality depends on being observed, then what exactly is the observer? What is this strange spark behind your eyes that notices the world, asks these questions, even listens to this soft, drifting story as your mind hovers between waking and sleep? Consciousness, the awareness that you are you, has always been one of the most stubborn puzzles in science. We can point to neurons firing, synapses flickering, chemical signals leaping across microscopic gaps. We can even see how thoughts are shaped by memory, language, emotion, and perception. But where does awareness come from? Why does a network of cells become a mind that wonders about itself? For centuries, philosophers, poets, and scientists alike have wrestled with this. Some argue that consciousness must eventually yield to a purely classical explanation, that it will be pinned down by biology alone. But others have wondered whether quantum mechanics might hold a clue. After all, if reality at its deepest level is fuzzy, indeterminate, and dependent on observation, then perhaps the observer, your mind, is somehow quantum too. It's a controversial, fragile idea, but one that keeps flickering back into the conversation, like a firefly in the dark. One of the earliest and most famous attempts to link quantum physics with consciousness came from the mind of Eugene Wigner, a Hungarian-American physicist who made pioneering contributions to quantum mechanics. In the 1960s, Wigner imagined a new version of Schrödinger's cat. In this version, there's not just a cat in a box, but a human observer in a sealed lab who measures the quantum system inside. From the outside, you, Wigner, have to describe the whole lab, observer and all, as a single quantum system. Does that mean the observer's brain, their entire conscious mind, is in a superposition too? Is their awareness both awake and asleep, both sure and unsure, until you open the lab and check? It was a mind-bending twist on the measurement problem. Wigner concluded that consciousness must somehow cause the collapse, that the mind, by being aware, forces the universe to choose. This idea, sometimes called the Wigner's friend scenario, is still debated today. Many physicists think it's unnecessary, that the environment itself, or the process of decoherence, explains why the world looks definite when we check it. But the puzzle lingers like a riddle on the edge of sleep. If measurement needs an observer, and you are an observer, does your mind help shape reality? Fast forward a few decades, and we meet Roger Penrose, a brilliant British mathematician and physicist, and Stuart Hameroff, an anesthesiologist fascinated by the roots of awareness. Together, they proposed the OR theory, short for Orchestrated Objective Reduction. It's one of the most famous and controversial quantum consciousness ideas. OR suggests that tiny structures inside your neurons, called microtubules, might be able to support quantum superpositions. Microtubules are delicate protein filaments that help cells keep their shape and transport materials. But Penrose and Hameroff argue that, deep inside these structures, quantum effects could persist long enough to influence how neurons fire, creating patterns of coherence that ripple across the brain. In this view, consciousness arises not just from the chemical chatter of neurotransmitters, but from quantum computations occurring in fleeting, shimmering pockets within your brain. Each collapse of these quantum states contributes to the flow of conscious experience, the moment-to-moment feeling of being you. It's a radical idea, and many neuroscientists remain skeptical. The brain is warm and wet, a noisy, bustling place. Quantum states are famously delicate. Even a stray photon, a tiny vibration of heat, can shatter a superposition. How could quantum coherence survive in such a chaotic soup of electrical signals? Yet experiments keep nibbling at the edges. Researchers have found that certain biological systems, like the photosynthetic processes in plants or the magnetic sense of migratory birds, appear to preserve quantum coherence in warm, noisy environments. Could evolution have discovered hidden ways to stabilize these fragile states inside our heads? So far, we don't know. But the question itself is quietly thrilling. It asks us to imagine the mind not as a clockwork machine of neurons alone, but as a shimmering bridge between the classical and the quantum, the certain and the maybe. For a moment, let's follow this idea further, not to claim it as truth, but to let it glow in your imagination. Imagine that your awareness is like a wave function, flickering between possibilities, collapsing gently each time you notice something new. Maybe this explains why thoughts feel so fluid, how ideas bubble up seemingly from nowhere, how intuition sometimes leaps beyond logic. Perhaps, if consciousness does have a quantum aspect, it helps explain the unity of your inner world. Billions of neurons fire in different places at different times, yet you experience it all as a single, seamless flow. A quantum process might allow distant brain regions to synchronize in a way that classical connections alone can't. Again, this remains speculation, a dream at the far edge of science. But even if consciousness is purely classical, there is something undeniably quantum about the way we experience reality. We see the world through limited eyes and make sense of it through probabilities and guesses. We can never be perfectly certain. Our memories blur, our perceptions shift, our sense of self changes from moment to moment. In a sense, your mind is a superposition of all the versions of you you've ever been. The curious child, the worried teenager, the laughing friend, the quiet observer lying here now. Each version flickers in and out, entangled with memories and hopes and stories you tell yourself about who you are. When you drift toward sleep, the boundary between conscious thought and dreaming dissolves, a bit like a wave function blending possibilities. Your brain generates vivid images, strange loops of time and place, feelings untethered from logic. Some neuroscientists wonder whether dreaming itself hints at the brain's deep capacity to juggle improbable connections, a biological echo of the quantum world's creative ambiguity. And whether or not quantum physics is the secret engine behind awareness, the metaphor itself is beautiful. It reminds you that your mind is not a static machine, but a living pattern of unfolding probabilities. Just as the double-slit experiment shows a particle exploring every path until it's observed, so too do you wander through choices and possibilities each day, your decisions collapsing the branches into a single thread you call your life. Perhaps that's the true lesson of the quantum mind. Not that we can measure its workings in neat equations just yet, but that consciousness itself invites us to accept uncertainty, to embrace the unknown, to dwell in the shimmering gap between what we can prove and what we can still imagine. So as you lie here, your breath soft and slow, your thoughts drifting like wave functions yet to collapse, let your mind settle into this gentle truth. You are an observer and the observed. A bundle of atoms governed by physical laws, and yet also a spark that notices, remembers, dreams. You are, in a quiet way, a paradox of your own, certain and uncertain, solid and fleeting, here and everywhere you might yet go. When morning comes and your eyes blink open, the mystery will still be there. The question of how mind arises from matter will wait patiently for another generation to puzzle over. But tonight, you can rest knowing that your awareness, fragile, astonishing, unique, is one of the greatest wonders the quantum universe has ever produced. Sleep well, quantum traveler. And if your dreams wander into strange places tonight, worlds where thoughts shimmer like particles, where possibilities split like branches on a cosmic tree, perhaps that's just your mind, exploring the deep quantum garden inside you. There's something deeply comforting about knowing what is real and what isn't, especially when you're lying in bed, drifting through a universe where reality seems so slippery. For all its strangeness and wonder, quantum mechanics has also become a fertile ground for misunderstanding. Somewhere between textbooks, pop science headlines, and late-night conversations under the stars, myths have grown like little mushrooms, feeding on the darkness of confusion. And tonight, as you relax, we can take a quiet lantern in hand and wander among these myths, seeing what they truly are and what they're not. One of the most popular stories people tell about quantum physics is that your mind alone can reshape reality. It's a beautiful idea. The notion that thoughts are so powerful they can collapse wave functions on the other side of the cosmos, that intention alone shapes the universe like a potter shapes clay. But when you peek more closely, you see something subtler and more interesting. In the quantum world, observation doesn't mean a conscious mind focusing its will. It means any interaction that forces a quantum system to choose a state, like a photon hitting a detector or a stray atom nudging another out of superposition. The universe doesn't wait for your awareness to snap into focus. It simply unfolds according to its rules, indifferent yet beautifully precise. Still, There's something hopeful in this misunderstanding. It reminds us how deeply people want to feel connected to the hidden workings of things. To imagine that our inner world can shape the outer world is comforting in an uncertain cosmos. And in a way, that feeling isn't entirely wrong. While your thoughts don't collapse distant wave functions, your choices, your curiosity, your experiments, they do shape what you learn, what you discover. You are not a cosmic puppeteer pulling quantum strings with your brainwaves, but you are an explorer who changes the map by walking it. Then there's the persistent dream of faster-than-light communication. Quantum entanglement, that wondrous phenomenon where two particles become so linked that measuring one seems to instantly determine the state of the other, has often been described as a cosmic phone line. A whisper between lovers light years apart, a secret shortcut through the universe's speed limit. But the truth is less dramatic, and somehow even more magical. Yes, entanglement is real, and yes, the connection between entangled particles does seem instantaneous, but the information you get is random. You can't send a message that way. There's no hidden Morse code in the spin of an electron. You measure spin up or spin down, but you can't choose which one you'll see, and you can't force your partner to see what you want them to see. The universe preserves its speed limit, even as it allows this silent bond to exist. If you think about it, that's strangely comforting. Entanglement tells us that parts of the universe can remain connected in a profound way, no matter how far they drift apart. But they do so in silence, without betraying the fabric of cause and effect. It's not a shortcut for gossip or secrets. It's a gentle reminder that distance is more complicated than it appears, that separation is never total. And who could forget poor Schrodinger's cat, so often imagined as an undead mascot for quantum weirdness? People love to say that the cat is both dead and alive, locked in a ghostly limbo until the box is opened. But this was never meant to be taken literally. Schrodinger's thought experiment was a way to poke fun at the absurdity of applying quantum principles to big things. In reality, a cat, warm, breathing, purring, is constantly interacting with its surroundings. Air molecules bump its whiskers, vibrations hum through its fur, photons bounce off its eyes. All of this environmental noise collapses any potential superpositions long before you lift the lid. The cat's fate is sealed by the universe's messy connectedness. So no, there are no half-dead cats haunting the quantum realm. Just an elegant lesson about how small-scale phenomena blur into large-scale certainty. And what about the idea that quantum physics is pure randomness, a cosmic dice game that rules out any order or predictability? It's true that quantum mechanics tells us some things are inherently uncertain. We cannot know both the exact position and momentum of a particle. We cannot predict the moment a radioactive atom will decay. But randomness here is not chaos. It's statistical elegance. The rules that govern probabilities are so precise that we can build computers, lasers, and MRI machines that rely on their reliability. It's as if the weather in a place you've never been always dances within predictable patterns. You don't know if it will rain at 2:03 p.m., but you know the seasons, the trends, the curves of probability. Quantum physics is random only up close, but zoom out a little and patterns emerge, beautifully robust. Then there's the myth that anything is possible. That because particles can tunnel through barriers and exist in superposition, we can have quantum levitation of your car or teleportation of your coffee across the kitchen counter. But again, The universe is more disciplined than that. Quantum phenomena come with strict rules, conservation laws, energy constraints, mathematical fences that keep possibilities from running wild. Tunneling is real, but you won't be phasing through your front door anytime soon. Superposition exists, but only for systems small and isolated enough not to decohere instantly. The same quantum mechanics that makes particles so strange also makes them reliable. It builds the world's structure, brick by shimmering brick. Still, these myths, half true and half wishful, tell us something about ourselves. They show that we hunger for connection, for mystery, for a sense that the world is not closed off behind glass, but open to our curiosity. And maybe that's the deeper truth worth keeping. While your thoughts won't bend the laws of physics, your questions do illuminate them. While entanglement won't let you whisper across galaxies, it does remind you that separateness is not always final. While the cat is never really both dead and alive, your imagination can hold two possibilities at once, and that's something precious. So as you lie there, your breath soft and steady, let these myths drift through you like passing clouds. Let them remind you that the truth is often stranger and more beautiful than any rumor. The universe doesn't need your thoughts to bend its particles. It just needs your wonder, your willingness to look deeper than headlines and sound bites. And notice how, even in clearing away the myths, we find poetry in the reality that remains. Quantum physics does not say that you control the universe with your mind, but it does say that your mind is woven from the same fabric as the particles that dance and tunnel and interfere. Quantum physics does not grant you a shortcut to faster-than-light messages, but it does offer you a glimpse of non-local bonds that persist across emptiness. It does not promise that you will vanish through walls or hover above your bed, but it does remind you that you are already part of a world built on invisible fields, ghostly probabilities, and delicate certainties. Sometimes, clearing the fog is the greatest comfort of all. Myths come and go, but the real quantum world remains, humming just beneath your pillow, threading through your dreams. It is a world of maybe, of probably, of sometimes. And yet, out of this shimmering uncertainty comes the solidity of your breath, the warmth of your blankets, the steady beating of your heart. So if you find yourself ever tempted by stories that promise impossible things in the name of quantum, smile gently. Remember that the truth is already a miracle. Atoms that obey rules so precise they built your bones. Particles that swirl through you in coherent waves. Forces so finely tuned that your very existence is possible. There is magic in this. Real magic. The kind that doesn't need exaggeration. The universe is quantum all the way down and all the way up. Take a deep breath. Let the myths drift away like mist at dawn. What remains is not less wondrous for being real. It is more. Because in the quiet corners of the quantum world, the story is not about bending reality with your mind. It's about the simple, astonishing truth that you are already part of something far stranger, far more intricate, far more deeply connected than any myth could ever promise. And that is enough. And as you let these thoughts settle, you might feel the gentle pull of sleep drawing you closer. The myths slip away, the misunderstandings dissolve, and you're left with a soft sense of awe for a universe that asks you to wonder, not because you control it, but because you belong to it. So close your eyes if you haven't yet. Breathe in the real, the true, the quietly astonishing quantum world that wraps you like a blanket of maybe and drifts you ever so gently toward your dreams. It's funny how the more we learn about the quantum world, the more we're asked to hold contradictions gently in our minds. We've wandered through wave functions and entanglement, peered into the delicate ways life itself might harness quantum tricks, and we've cleared away the fog of myths that cling to these ideas like morning dew on grass. And now, here we are, you and I, lying in the stillness of the night, wondering what all this really means for us. Not as physicists or philosophers, but as living, breathing beings woven into this shimmering web of probability. Sometimes, the best thing we can do at the end of a journey like this is to simply rest in the wonder of it all. To think that, long before you or I were ever here to question it, the universe was already dancing to a quantum beat. Tiny particles tunneling through barriers they should never cross, atoms forming bonds that hold your bones together, the stars above you fusing elements in their hearts thanks to a bit of quantum trickery we call tunneling. It is humbling to realize that you are not just observing these phenomena from the outside, you are made of them. When you inhale the quiet air of your room tonight, you might picture the oxygen molecules bouncing around, their electrons clouding in orbitals, obeying the exclusion principle that keeps them from collapsing into chaos. When you close your eyes, think of the photons that traveled from the glow of your lamp through the lenses of your eyes, triggering signals in your retina, an everyday miracle made possible because light is both wave and particle. When you drift toward sleep, you can imagine your neurons firing in tangled webs, their chemical bonds and electric signals dancing on rules that, at their deepest level, are quantum. But what does that mean for you, really? Maybe it means that the world you trust, the ground beneath your feet, the warmth of a hand held in yours, is built on something beautifully uncertain. It means that certainty is never absolute, and yet from that uncertainty comes everything solid you hold dear. It means that you, an intricate collection of atoms and molecules, are not just a passive witness to the universe's story, but a living chapter in it. And maybe that's the most comforting thing of all. You don't have to understand every equation or memorize every interpretation. The fact that the universe allows you to exist, to wonder, to dream, that's enough. Your breath tonight is possible because electrons orbit nuclei in precise shells. Your heartbeat is steady because quantum rules make molecules hold together, cells divide, enzymes find their marks. Your mind drifts through thoughts because of synapses firing, chemicals released and received, all riding on the backs of tiny particles whose behavior defies simple logic yet makes sense in the grand dance of things. This idea that life and the quantum are not separate but deeply intertwined invites you to see yourself differently. Not as a stranger to the cosmic stage, but as an actor who is the stage itself. Every cell in you holds secrets traced back to the moment the universe began, when quantum fluctuations in the early cosmic foam created tiny differences in density, seeds that would grow into stars, planets, trees, people. In a way, every laugh you've shared, every tear you've shed, every dream you've dared to dream is rooted in a quantum possibility that wavered and collapsed into reality, forming the path that brought you right here to this quiet moment. It's a tender thought, isn't it? That all the things you feel, all the hopes that carry you through your days, have foundations deeper than any philosophy, more ancient than any myth. Quantum mechanics reminds us that the universe is more like a whisper than a shout. It's subtle, uncertain, alive with potential, and it invites you, gently, to lean into that mystery without fear. Sometimes people think that understanding quantum physics steals the poetry from the world, that once you know the cat isn't both dead and alive, that entanglement can't carry secret messages to distant lovers, the magic fades away. But maybe it's the opposite. Maybe the real magic is that these tiny particles, these probabilities and wave functions, come together to create everything we hold dear. The smell of bread baking in the oven, the warmth of sunlight on your skin, the thrill of a kiss, the ache of missing someone, all made possible because electrons refuse to occupy the same space, because particles tunnel through barriers, because atoms bond in just the right ways. When you see it like this, the magic deepens. And perhaps that's what makes the quantum world feel so close, even though its scales are so small. It lives inside you, beneath your thoughts and bones, yet it also stretches outward, building galaxies from particles that once flickered in and out of possibility. There's no border between the quantum and the classical, just a gradient where the fuzziness of probabilities settles into the solidity of things we can hold and touch. You are that gradient, a bridge between the certain and the uncertain, the possible and the actual. So, what do we do with this knowledge, lying here in the dark? Maybe nothing at all. Maybe it's enough to just know that you belong to a universe that is not cold and rigid, but soft around the edges. A universe that says, I don't have all the answers ready for you, but you're allowed to wonder. A universe that asks you to stay curious, to keep peeking into its hidden corners, to remember that even the smallest piece of reality hums with possibilities. And when life feels confusing or uncertain, when the ground beneath you feels less solid than you'd like, you can remember that it's supposed to feel that way. Certainty is an illusion we build for comfort, and it's a good one, a necessary one. But deep down, the universe is built on maybe, and somehow, out of that soft maybe, it created you, perfectly uncertain, perfectly real. Tonight, as you drift closer to sleep, you might feel the soft weight of that idea settle into your chest like a warm blanket. You are not separate from the quantum world. You are its expression, its question mark, and its answer all at once. The stars above you shine because particles tunnel through energy barriers. The sun rises because fusion happens in defiance of classical logic. And you rise each day, breathe, love, laugh, and dream, because the laws of quantum physics say it's possible. So breathe in. Let the last lingering thoughts of the day float away. There is no need to solve the universe's mysteries tonight. There is only the gentle truth that you belong here in this moment, part of a story that began in a quantum fluctuation and continues in the soft beating of your heart. May you sleep well knowing that the world around you, this vast, shimmering quantum universe, is stranger, kinder, and more beautiful than any myth could make it. May you carry that wonder with you into your dreams. May you wake tomorrow with the same quiet curiosity that brought you here tonight. And when the morning light comes, may you remember that beneath every surface, behind every breath, the quantum world hums its secret songs. And you are part of that melody, no matter where you go, no matter how the day unfolds. Thank you for sharing this calm adventure with me tonight, here on Boring Stuff. I hope you drift off feeling light, curious, and softly connected to the hidden patterns that hold you. Sleep well, dear listener. Good night.